This video is for Chemistry in the Earth System, Unit 3.4, Lewis Structures and Molecular Geometry. Today's essential question is, how are Lewis structures and VSEPR theory used to predict the polarities, geometries, and bond angles of covalent molecules? Our first main idea, the VSEPR model. VSEPR stands for valence shell electron pair repulsion. Because electrons all have negative charges, they repel each other. That is why the electrons and bonds in Lewis structures are spread evenly around the symbols. That is also why electrons don't pair until the valence shell is more than half full, if you remember your orbital diagrams. Now remember that Lewis structures are simpler than real molecules in several ways. For one thing, Lewis structure diagrams are always two-dimensional. The VSEPR model considers the third dimension instead of a flat plane. VSEPR theory explains that electrons can actually move in all directions, and this allows them to move even farther apart. Consider this Lewis structure for methane, CH4. The angle between the bonds in the drawing is 90 degrees. The true shape of CH4, however, is three-dimensional. VSEPR shapes are based on the geometry around the central atom of the molecule. Again, considering the central atom of the molecule. The bonds in methane actually form angles of 109.28 degrees. The hydrogen atoms are at the corners of a three-sided pyramid called a tetrahedron. The angle between the bonds is called the tetrahedral angle. The shape of a methane molecule is therefore known as tetrahedral. Now consider the Lewis structure of water. We can expect that all the electron pairs will repel one another, whether they are bonding pairs of electrons or non-bonding pairs of electrons, aka lone pairs. However, the repulsion between non-bonding pairs, or lone pairs, and other pairs of electrons is stronger than between two bonding pairs because two nuclei are exerting a pull on the electrons in a bonding pair. The angle between the bonds will increase, and in this case, to 104.5 degrees due to this extra repulsion. Because there are only three atoms involved, the molecule won't be a tetrahedron. The shape of the water molecule is therefore known as bent, or sometimes angular. To incorporate VSEPR theory into your diagrams, first draw the Lewis structure of a molecule, and then mentally picture the bonds and electron pairs moving as far away from each other as possible. Our next main idea, bond angles. Combining Lewis structures with VSEPR theory, we can determine the bond angles and geometry of a molecule. We can also use this information to tell whether it is a polar molecule or a nonpolar molecule. In general, there are three situations to consider. 1. A molecule can be nonpolar because it has all nonpolar bonds. 2. A molecule can have polar bonds, but still be nonpolar because its dipoles are arranged in a way so that they all cancel each other out. 3. A molecule can be polar because its geometry causes one part of the molecule to be more electronegative than the other. Oxygen, O2, is an example of a nonpolar molecule with nonpolar bonds. Carbon dioxide, CO2, is an example of a nonpolar molecule, but with polar bonds that all cancel each other out. In this case, the bonds are polar, but the molecule is not because the 180-degree angle of the bonds. Water is an example of a polar molecule. The angle between the bonds thrusts the electronegative oxygen atom to one side and the less electronegative hydrogen atoms towards the other side. The result is an electron-rich side of the molecule, which has a slightly negative charge. Let's take a look at a sample problem. This chart, among many others, shows the possible molecular geometries that compounds can show and the resulting Lewis structures. These geometries are governed by VSEPR theory and bond angle. So, what are the geometries, polarities, and bond angles of ammonia, NH3, and of the ammonium ion, which is NH4 plus? Well, the Lewis structure, as we saw before, is shown on the screen here. The nitrogen to hydrogen bonds are all polar because the electronegativity difference is greater than 0.4. Because the electron repulsion, the unbonded electrons and the three bonds of NH3 will form a trigonal pyramidal molecule. Now, since the electrons are not part of the molecular structure, the shape will be a flattened three-sided pyramid. NH3 will be polar because the side with the unbonded electron pair is more electronegative than the other three sides. Now, to move on to the ammonium ion, all of the bonds are polar, but equivalent. They will be separated symmetrically by tetrahedral angles. Although they are all polar, the dipoles will cancel to produce a charged, nonpolar ion with a tetrahedral shape. At this point, you should be able to generate a full and appropriate response to today's essential question. How are Lewis structures and VSEPR theory used to predict the polarities, geometries, and bond angles of covalent molecules?